Okay. Uh, so I suppose that you should have submitted the assignment, right? The last assignment about using stochastic gradient descent to iteratively update the logistic regression. Okay. If you have not, please submit as soon as possible. Okay. For today's lecture, we are going to look at the formation of the deep forward network or the neural network and the algorithm called backpropagation, which is, I would say, the workhorse of deep learning that use gradient descent incorporating with different strategy for optimization in order to update the network weight in such a way that it can minimize the errors that it produces in each iterations. Okay, and so particularly for today's lecture, we are going to look at the mathematical side of the deep forward network, and also the backpropagation algorithm, and also the implementational side using Keras. Okay, so let's begin. Deep forward network has another name called the neural network, or the artificial neural network, or just neural network. Right, back in, I would say, in 1999, in about the year 2000, even when you call the topics of neural network, sometimes you may refer to the biological study of the brain of the neural network itself in the neuroscience study. But nowadays, when you mention neural network, it is often refers to the technique that allow you to build an AI, that allow you to create an automatic learning function that could capture variations between input and output, and then make use of those variations, make use of those patterns to make prediction, to make judgment. Okay, so it is called the feedforward neural network, multi-layer perceptron in 1990. So the idea of the model is to approximate a function. I used to call this a functional model, because you are creating a model that describing a functional mapping between input and output. In this way, you are, for example, you can create a classifier y equal f star x when you have x and y as input and output, and then you're trying to learn function f that could map between the two, right? Now you can think of many things that could be done in this way. You can create a model that map between speech and text in such a way that you create a speech recognition system. You can create a system that receive a signal, a brain signal, and then action. Then you would have a model or system that could interpret the thought and make action. You can create a system that take in image and then recognize whether that image, that fingerprint, belong to you or belong to the authors. Okay, so as you can see that there are variations of things that you can do with such a model. Well, initially, I would say the first iterations of the neural network is to just stack them up to have multiple logistic regression, multiple model work together, and trying to, I would say, using the many model to do the job instead of just one. So it is a model that trying to map from x with certain parameters, the weights, to y values. So the idea of the model would be to learn the parameters, which should be describing the behavior of how to interpret the data, how to transform the data into the domain that can be utilized better than in the original domain. Okay. Now the word feedforward may have its rival, I would say, may have its opposite. I don't think it's opposite, like it's pair. Like you might have heard, like there's a feedforward model, the model that feed from input to output, and there is also a feedback model, the model that take output and then feed it back to the input. This is known as recurrent model. The recurrent neural network is one of such a model that take into account of the of the output that it produced, and then use it to remember the previous state, so that you can create a model that can adjust, that can, I would not say adjust, I would say that utilize the computation based on the state that is in at that moment. We will look in that in more detail in the topics of recurrent neural network. Okay, when we talk about network, particularly it has, well, obviously it must have multiple nodes. It must have multiple entities that connect to one another. That's why it is called a network. Okay, so the feed-forward neural network is called a network because it composes of many functions, many models that interconnect to one another. So you can think of it as a chain of model. That is, you have the model f1x, and then f1x is mapped to f2x, and then from the f2x, f3x, and so on. So you have like multiple layers of model that map from the output of one model and then use it on another model. Okay, these chain structure are usually called the neural networks, which we will see in a moment on the diagram on the components and some of the notion that you should know. That will be the critical component in neural networks there. So in the chain structure, input from the original input x would need to be transformed by each layer of the network. Right, the F1 here is the first layer of the network. Once it transforms input, you get the output of the first layer, which is fetched as input to the second layer, F2, right? And then F3. So each iteration here that it fetch output from one layer to another layer, right? We usually refer to this as the depth of the network. Right, or how deep the network is determined from the layers that it contains. Okay, when this layer is deep, it is called deep learning because you have like so many layers of network, so that it can transform the data into another domain and utilize this domain transformation in representing the data. We'll see about that later on. Okay. Finally, once it reaches the output, this is called the output layer. The output layer has to have format match with the output that you want to predict. Okay, and the inside F2 and F1, these are called hidden layer because they are inside. Right, we cannot see the in how they work. We can determine how it works, but we can extract feature map, we can extract layer out, but it is hard to interpret. So the model can decide to take one path instead of another, so that it can remember, it can penalize, it can determine which input are important. Okay, so with this, it can determine like latent factor or the hidden pattern within the data. Dimension of the layer of I would say the number of nodes in each layer is referred to as width of the model. So in the network structure, we should usually refer to it as this in this way. The depth is the number of layers that you have, and the width is actually the number of component, the number of model in each layer. The width of each layer would be different, and it depends on the architecture as well. When we talk about feed-forward network, we see the network like this. But next time when we look at the convolutional, I think it must be maybe next 2 weeks, I think, because you have to do assignment about this first. In 2 weeks, you will encounter the convolutional neural network, which at that point you will encounter like different architecture. You see how different thinking can lead to different architecture in the network, and then recurrent neural network, and then Siamese neural network, and then transformer. Different architecture would lead to different output, and each of them actually capture certain, I would say, intelligence, certain functionality, like capture memories, capture the attention, like cognitive function that we have, and then model them as the as the pattern mapping, as the model that can learn and then capture patterns, right? So maybe you have ideas about how to incorporate these cognitive function into the model, and then maybe you can come up with your own version, your own architecture later on, and that might be interesting to see. Okay, so layer 1, 2, 3 are hidden layers, and layer 4 is the output layer. Right? We have this input layer, which actually doesn't stand for, doesn't receive anything, just a layer that receives input in. Okay. So during network training, right, the FX, we try to train the models in such a way that Fx would match F star x. Fx is the output of the model, would match, we would drive it to match the actual output. Okay, but the estimation of output, the prediction, may not be that accurate, right? That's why we need to have a way to train the model. So that the output layer will produce the results close to the actual value, and adjust the weight, adjust the parameters in the model. But in this model, we would not specify exactly how it should be trained, right? Or exactly how the error should be propagated, right? Usually we would design on the flow of information, and then use algorithm like back propagation algorithm that can propagate the error back from the error in the output to adjust the weight in the input, and then let it learn by itself in that sense. Okay. All right. So the learning process is basically trying to adjust the model to predict the output, right? To match the output. Okay. And when prediction, sometimes there is a need to perform transformation. Particularly when we see the network structure such as this, you can see that there are multiple parts that are combined into just one node. That means that multiple signal has to come in, has to combine it, and it will create like a large reaction and maybe a large response in combination. But in order to denote it as whether this node is active or non-active, those large value has to be transformed into the value that are capped between certain range. That's why the use of sigmoid function it is very beneficial, because we kind of cap the value between 0 and 1, and then it make the model able to represent this as the activation of the neuron, and then in connection you have like the neural network in this sense. This function is called, actually we will see about it later, it's called the activation function. So in order to understand the idea of the multi-layer network better, right, think about it this way, that we have input x. Input x has to be transformed based on certain mapping function, this phi x. Why do we need the transformation? Sometimes input x cannot be separated. If you want to do classification for the output of XOR function, for example, you cannot draw one line and then separate them out, right? You cannot draw one line. You need to have multiple lines. Or for example, suppose that your data looks like this. Your data looks like this. How can you draw a line? A line that separate the cross mark from circle marks. Well, you will not be able to, right? That's why. But if we were to transform it, into another domain, just like in SVM. In SVM, there is a kernel function that you can transform everything into like a slope of the mountain. Then you use just one plane to cut the mountain. Then you can get that result out. But in neural network, we would not specify such a function as the RBF or something like this. We want the system to learn that function by itself, to learn the representation, to learn how should we transform the data, to have like the best feature representing the data in order to do certain tasks that we want. Okay, so such transformation function for the deep learning need to be specified on how it should be transformed in order to match the task that you want to do. In the early day of machine learning, if you want to do, for example, fingerprint recognition, face recognition, you need to think about what features that you want to use. You might need to do edge detection, and that will incur some types of errors in the edge that it's detecting. You might think about a way to detect a certain circular patterns within fingerprint, and that also has certain errors. So feature extraction in the early days are quite biased, and it is okay. So to a certain extent, you can use system to match it, but with the deep learning that it learned the best representations from the dataset, it allows us to let the system extract the best features by itself and then use them in classification within the model in such a nice way that it is modular. It is in just one model that it can also extract feature and then use it to do the job itself. Okay, let's look at some example here. For a function like XOR, exclusive OR, the function XOR say that we have like two values, x1 and x2 as input, and the output can be 1 or 0. You know that the XOR function, if input are the same, then the output would be 0. If you have 0 and 1 or 1 0, you get the output as 1. Okay, so this is the XOR function, and we want to train a model that could perform the XOR function, right? That could learn the XOR function from this data and then perform XOR prediction using XOR. Now let's look at this. Suppose that we are going if we are going to solve this using linear regression, just like the above. Say we use linear regression, we have the weight. The weight is multiplied to x and then plus the bias and get y, and the loss function would be the sum. This is the mean square error, right, MSE, taking derivative on the mean square error. So for the output, just look at this. How would you draw a line that separates 0 and 1 from one another using just one line? Is that possible? Think about it. Can you draw one line that separates 0 from 1? One straight line, mind you, right? Not not the curved one. The curved one is quite complicated. Right? One straight line. Can you do it? Of course not, right? It's actually difficult to do with just one line. If we have weight equals 0 and b equal 1/2, then the output would always be 1.5, which is not good in classification problem in this case. So how do we address this? What types of network that could be able to predict the XOR function? Right. If one model is not enough, then the layers of network actually could do the job. And the reason why it can handle such job will be revealed in the subsequent slides, like how it transforms the data into those domains. Take a look at this first. In the feedforward network, we have input x1 and x2, and x2. Then they are fetched into the first logistic regression model and the second logistic regression model, and each of these are fetched to the final output layer here. So think about it this way. Suppose that we think about layers as just one operation. When you write it like this, this is like h1 is like summing, right? It's like summing the data. Like you have the weight here, weight of x1 to h1, x2 to h1. The weight of x1 to h2, x2 to h2. And the computation here would be matrix multiplication. That is, you have the vector x. Then what you want is to multiply the vector x with the weight w. W would be the dimension of x and h. Right? It depends on x and h, so it will be the size of x times the size of h. Right? And then you would get the state vector at h. This state vector can then be multiplied with the weight w, and then get the result y out. Right? So we now have two layers of network. Right? For the first one, we have the f1 that receive x and have parameters w and c. Right? Think about it as this model that you have f1x equal w transpose times x. And in another layer, the f2h, it received as h because this is like the second hidden layer here. It has the computation is h transpose and w. All right, and then you get the final result out. Right, as the two layers, the output from the two layers that are kind of feeding from the initial layer, from the input layer to the output layer. In summary, if we look at this computation of the function, we have the final output as w transpose w and the capital W transpose and x, right? So this can be represented as x transpose and w, where w is actually the combination of the two, right? So it means you can just compute it one time for the linear function like this, and if you look at it this way, it doesn't have an ability to transform at all, because even though you have two layers, in the end it's just one layer here, right? This is just one layer, just x, then multiply with certain vector. It's just a simple linear regression once you combine them together. So having two layers of linear regression is not a good idea. It doesn't solve the problem. There must be a way that to transform the output of each layer so that it is not linear. It can represent different things. And that comes the activation function. The activation function allows neural network to learn nonlinear pattern just like XOR on the other types of network. It used the F5 transformation of the output of the model of the computation to the capped output, right, to fixed output level. Okay, so that's the function. For example, for the XOR, we can have this G and then receive the computation here to be the activation function. This G would transform the sum. This, if you interpret this is just the sum, the combination sum of x plus c, and then put it into certain activation function, certain function that would transform the whole vector here, element by element. Okay. So the multiplication here would result in, for example, for XOR, it results in 1 times 2 vector, and then once you apply the transformation, you also get this HI, right? HI out. So it means that this is element-wise transformation. There are different types of transformational function, right? The original one would be the one that we use in logistic regression, the sigmoid function. But now today, the modern neural network, sigmoid function has certain limitations, I would say. It has a limitation in terms of the large gradient and the small gradient are not well represented. So there is a better way that will propose, like this ReLU, the rectified linear unit, or the latter version, the leaky one, and the other modification which I will not cover here. Let's talk about ReLU for a bit. ReLU or rectified linear unit has the activation function like this. This which is the GC, which is 0 if it's less than 0, and equal to C, equal to just that value when it's more than 0. Can anyone tells me what is a nice mathematical properties of ReLU? Solve plus. Let's talk about mathematical properties. Just look at this function. What is the nice mathematical properties of this ReLU? Just like in sigmoid. In sigmoid, when you want the derivative, just get the value multiplied with 1 minus itself, you get derivative. How about this one? What is the nice property? Sure, negative will be 0, and another thing, and the positive would be linear. If you dip the linear function, the result is 1. Right. So if you take derivative of the positive side here, you get the value of 1, which is nice because it's just value of 1. You don't have to compute anything, right? So that means it would even simplify the gradient calculation, reduce the number of time complexity required to do the computation. Okay. So any of you want to research on the paper regarding the activation function, feel free to do so. There are quite a number of them that worth take a look at. But I will just cover this one because there are so many other things I have to cover here. Okay, once we have this rectified linear unit, we can plug the value in. That means the output of the first layer, now instead of having the value of W transpose X alone, it becomes the 0 or W transpose X plus C. And finally, at the end is W transpose times this vector plus B. Okay. Now let's make certain assumptions of the learned model and then see what happens when we put in an input into the system. Let's say we have W as a matrix of 1. C, which is a vector that compute during the hidden layer, has the values of 0 and minus 1. W for the output layer has the value of 1 and minus 2. Right? We have this value, and then we have a bunch of input here. Let's calculate this iteration by iterations. I should say the layer by layers. First, we have X here, X 0, 0, 0, 1, 1, 0, 1, 1. You know the XOR function. Now let's multiply X with W. I would write here XW here equal 0, 0, 0, 1, 1, 0, 1, 1 multiplied by 1, 1, 1, 1. Okay. So that means the first one and the first one, well, that's obviously these are 0 and 0. And the second row and first and second, you can see that they are 1 and 1. That's why we got this and this and 2 and 2, right? So this is the multiplication of X and W. Then this one is 0, 0, 1, 1, 1, 1, 2, 2 plus C transpose. Let's look at C. C is 0 and minus 1. Plus C, sorry. It's actually plus C. Not C transpose. It's supposed to plus C. Right? This is C transpose or C? C transpose would be, yeah, that's correct already. Plus C here. Plus C transpose here, 0 minus 1. Think about broadcasting, right? So when you perform broadcasting, sorry, I should write here and delete it, remove it. For this one, you have value of 0, 0 plus 0 and minus 1, you get 0 minus 1, 1, 1 plus 0 minus 1, you get 1 and 0, right? So you got this after that. And then for each of these value, it need to be tested. So ReLU actually just clip the value that is less than 0 to be 0. So there is only one value, this value. Only one value that is less than 0. So think about value here as the value at the hidden layers for each input. When input is 0, 0, we have the value at hidden layer as 0 minus 1. When input is 1, 1, we have value at hidden layer as 2 and 1. Okay? And if we were to put this into activation function, anything less than 0 would be 0. That's why minus 1 becomes 0. And we got h. Then multiply h with w. So this is 0 and 0. Multiply with 1 and minus 2. You get 0, 1, and 0. Multiply with this. You get, this one and this one, you get 1. 1 is 0 again, you get 1. And 2 and 1, this would be 2, this would be 1, you get 0. Okay, so now you can see that transformation, now the model can learn XOR function. It can produce XOR function once it has this value, once it has the activation function. But what is really happening? Right, what is really happening? Look at this. Initially, we have the input that looks like this. 0, 0, 0, 1, 1, 0, and 1, 1. After these input were transformed at hidden layer, let's look at what happened. Comparing it to this, let's look at what happened. 0, 0, 1, 0, 1, 0, and 2, 1. This is the original X space. Let me draw, let me put the vector beside it so that you can remember the matrix beside it. 0, 0, 0, 1, 1, 0, and 1, 1. After transformation at the hidden layer, it becomes something like this. It becomes 0, 0, 1, 0, 1, 0, and 2, 1. Zero, zero, 1, 0. Right? Let's check it. 0, 0 here. 1, 0. This one. And 1, 0 again. And 2 and 1. This value. So can anyone explain to me what happened here? Turn on the microphone and speak. That's fine. Type in the chat. It's okay as well. What happened? Oh, and by the way, once we saw that there is this learned edge space here, now we can clearly draw a line. Draw one line that separate 1 and 0 from one another. My question is, what happened in this hidden layer? What are these phenomenon? How X now is become something like edge? And what is the significance of this? Basically just explain to me what happened with this slide. Any idea on what has happening? And this would be the explanation of the whole deep learning, the whole neural network stuff, why it works. Yeah, I will wait for some explanation for this slide. Come on. H is learned by Lelu Max. Not really explanation. Put it in a layman term. What happens to a layman wouldn't look at XOR here. Well, in computer engineering term would define what happened to X. Well, from the original space to the transformed space, what is happening? Remember that I asked you that whether you can draw a line in the original X to separate the data into two parts. Can you? Maybe you can draw a line like this, right? Well, it's not a straight line. Oops. H is a new representation of X. That's correct, right? H is the representation, the transformation, the feature that were extracted from X. And these transformation from the original X space into the H space are learned automatically, right? So this is one of the idea of neural network and deep learning, that it allows you to transform the data from one domain to another domain, that it's easier to work with, right? It trying to do the thing that human also do, like select and detect the feature automatically, and then distinguish and then perform the function in that way. Okay, good. Right. So and that would lead to the learning of representations. Learning of the representation that we can use to perform classification, face recognition, image recognition, and many other deep learning stuff. Okay. Now you can see that that means the design of the network is very important, right? But in terms of training, if we talk about just the architecture of the feedforward, the training of the neural network is not different from the other machine learning model. We can use the gradient descent to train the model. So we can apply the gradient-based learning, right, to optimize the cost function, and so that it have the better version of the model. So what should be the cost function? This cost function will be similar to the linear model. We can use the maximum likelihood estimation, trying to match between the distribution of y. The model should be able to predict the distribution of y out. Okay, that means we can use either the cross entropy if we perform classification, or the cross entropy, or the error, some square error, the mean square error, in order to do the regression, right? You can do both, depending on the output, what types of output we are talking about. For example, if the output is a Gaussian output, it's distributed in a normal distribution manner, then this is there shouldn't be any nonlinear. You should have like the Gaussian linear unit, the Gaussian output. That means the output should have distribution of the normal distribution at the output though. For the input, it should contain the same transformation, the same the same nonlinear transformation of the activation function. But the output need to match, so that it should have like normal distribution between y and the parameter, like the y that predicts. So the error should be normally distributed. That means we can optimize it using the mean square error, and if you remember, we have those gradient derivation of the mean square error, the sum square error in the previous lectures. So the same here. If the output is binary output, 0 and 1 output, that means the output need to predict the label, whether it is 1 or 0. then we can, instead of having the linear output, we can then transform the output using sigmoid. Because sigmoid has the range of 0 to 1, that means we can now transform the linear output to probability output. And that's it. We have the output as the probability, and then we can match it to using cross entropy, the binary cross entropy, to train the model. Now, if the output is multi-nully, you have like multiple node, multiple output that are possible, then the training of the model, say you have discrete variables and possible values, it has to take one, then it means that the output layer contains multiple probability y, prop of y equal I, can be 0, 1, 2, 3, 4, 5, depending on the combination or depending on the category, level of categories that the model has. Give me next that. And in order to maximize that, the function at the end has to represent probability as well. And in order to do so, there is a transformation function that allows you to do that by using this, the softmax function. Right? The softmax function take z, which is linear combination, and it's exponential, and then divided by the normalization factor, summation of all exponential of different classes. That's why the softmax z at the end, when you sum them all, you will have the value equal to 1. Right? So think of this as the probability of each piece of the class that you want to predict. Okay, this softmax function can then be derived as the function that to be used as the as the log loss, as the loss function. Okay. So what we want to do in order to maximize the probability, remember that we want to maximize probability of that class in the maximum likelihood. And so in order to do so, what we need to do in this case, in the softmax case, we need to perform maximization of this logs of softmax and z. And now let's look back here. This is exponential and the summation of exponential, right? So if we were to take the log operator, this would be the z would be taken out, right? You got only z here, and this is linear value, and minus log of the summation of the exponential of zj here. Let's interpret this a bit. For correct prediction and incorrect prediction. For the correct prediction, what would happen? The log of softmax in the correct prediction. That means you get the correct class, right? The correct class, the zi. Then the pop of ci would be large. The z would be large. Value of z would be large before taking log. And this minus of log and the summation of the exponential of z. Let's think about the ideal case. This is large value, and here the exponential of zj here are very, very, very small value, right? They are very small value, so that when you take log of this small value, it becomes negative value. Negative plus negative encountering with negative, you get positive value. That's the log softmax would indicate that, okay, this is correct prediction. Now let's imagine the case that it is an incorrect prediction, right? What would happen? This would be low value, right? Ci will be very low value. This is incorrect prediction because, well, it's supposed to be the class I, but the probability is low, so this would be low value. But there would be value in the zj here that is large, and when you have large of the, let's say it dominate the whole thing, large of the exponential and log, and then you got zj that is large, and this is small, log of this value would be minus value if it is incorrect. Okay, that means the latter part kind of penalize the earlier part. Then so basically, simply speaking, you get negative value if it is incorrect prediction, positive value if it is correct prediction, right? So the idea is to maximize this log of softmax in order to to optimize the model, and then it goes to the MLE derivation and get the update function there. Okay, so these are the output layers. Okay, we will talk about each of the component of the networks here that we talked about earlier. We talk about output already, then hidden layer, then input layer. Okay, the next is hidden unit. The hidden unit, actually, they are still actively in research. There are many proposals. You can pick this as the research paper that you will look into to present at the end of the semester. ReLU has been used a lot, quite a standard there. But there are other model, other hidden unit that behave similar to this one as well, and maybe better, like the leaky ReLU, which address the problem that if you have negative gradient, and in the ReLU it would just penalize it out. You just clip it out. You might want the model to adjust a bit in that sense. Okay. So it will be in the form of activation function, the GC. Okay, why not using sigmoid as the hidden unit? The hidden units are the unit that inside the model. Like we are talking about the output layer and then the hidden layer, the hidden unit. In the hidden unit, there are many types of activation function that can be used, but sigmoid is not one of the good idea to use. The reason is that if you use sigmoid, then there is a potential that you would because when you have high value, then Z would be very positive, but the gradient would be low. When you have very low value, very negative Z value, it is also saturated, and it would not contribute to like a large gradient to adjust the model because it's very wrong. So because of that, this makes gradient descent a little bit difficult to deal with. But when you think about the ReLU rectified linear unit, if you have a large positive error, then it will correct the model. It will penalize the model heavily according to the contribution of the error that it has. So it would make the model adapt faster to learn the patterns. Okay. Right, so this is the reason that sigmoid is not being used for the hidden layer. Okay, now let's look at the architecture of the network. Right, when we talk about the output, the iteration function, hidden layer, now the overall architecture. Neural network can be organized into different types of architecture. The one that we are talking about today is the basic architecture called the feedforward architecture, just like down here. This is the feedforward architecture. We have the first layer, receive input, compute H1 act as input to the second layer, produce H2. So these are the architectural layer of the network, which in Keras and in TensorFlow as well, you can arrange this architecture and build the network, build the model easily with that. Okay. So why deep learning? Okay, the concept of deep learning is not new at all. There has already been the certain postulation that if you were to increase the complexity of the network to be large enough, right, it should be able to model anything. Okay, there is the theory called universal approximation theorem, that if you have a feedforward network, with a linear output layer and at least one hidden layer with certain squashing function, this can be approximate to any Borel measurable function. What it is, I will leave that to further research. Say that it can estimate the set of functions, okay, that has finite output, provided it has enough hidden unit. So if it has enough hidden unit here, it can certainly estimate many type of functions. And the derivative of feedforward can also be approximate using the gradient descent here. Okay, so how do we interpret this theorem? If we have like infinitely wide network, right? Actually, it can approximate any function. Well, just like you have many models, then you fetch it to one model for one unit data. Obviously, it should be able to model the patterns. Right? So the interpretation is this. When you have a feedforward network with single layer, with sufficient hidden unit, but you have infinitely large scale of layer, it might still fail to learn the generalization correctly. Why is that? Because it might learn individual output. So say that you have this one as the estimation, and then you have like many layers here, and say 3 nodes of input. You can imagine that the model can remember for each node here. It can remember each value of the output. And when you're trying to use the model again, it wouldn't be able to generalize because it is overfitted with that, right? It will be difficult for the model with one layer to learn to generalize, to learn the patterns, because it doesn't have an ability to transform the data into, let's say, into a complex transformation, a complex domain, or in other words, to simplify the patterns in the data, teasing one patterns out of one another to have better representation. You will not be able to do that. Okay, so having a deeper model has certain advantages because the deeper model will work like this. This is from Montufar 2014. It works like domain mapping. So let's say if you have the data distribution that looks like this, and you want to, when you use deep neural network, what happened? It would transform the complicated surface into a simpler one. It would fold them together so that when it folds once, you get this simplified layer, the transformation of the point. When it folds again, you get a simpler, right? A simpler cluster of point, and then you can draw a simpler line to account for the patterns here. So this is the ability of neural network. It can transform input into the domain that better represent the data, right? That better represent the features of the model. So the deeper the model, the better in ability to capture patterns, right? When you increase the depth of the network, the model would have a better accuracy, an increase in accuracy to a certain point, right? Once it exceeds certain point, you know from the last lecture that it would become overfitted, okay? So the point that it's become overfitted can be demonstrated by looking at this one. These are the test accuracy, the test using the test set of 3 types of model. The green one here is the fully connected model. You can see that if you kind of use the fully connected model, number of parameters would be like 0.8 to 10 to the 8. So this is around 80 millions, 8 millions, 6, yeah, about 80 millions parameters. Okay, and you can see that accuracy is just about this one. If you use 3 convolutional, 3 layers convolutional neural network, then I think it's 3 layer, I guess. With the less parameters, it can perform comparable to the fully connected. But when you have convolutional neural network that is deeper, then the model can generalize better, can capture the pattern better than the one that is fully connected. It means that there must be a certain properties of the network, that of the architecture in the convolutional neural network, that allow the model to generalize better. And we will see about that in the lecture about convolutional neural network, on what properties of the convolutional neural network that make it becomes better than fully connected layer. And maybe you have an idea in your research to kind of spin a type of neural network out, and then using such of these properties and improve its performance. Now let's look at how to train the model. It's actually a gradient descent, so I will not ask you to do this again. It's actually the gradient descent. So it requires two steps. First is the forward propagation, and second is the backward propagation. In the forward propagation, we have the weight, we have the bias, and input and output. So for forward propagation, we start with the input layer x as h0, and then do the for loop for the first layer to the last layer. And for each layer, we calculate the a, which is like intermediate value, put it into the AK, put it into the squashing function, activation function to get HK at each hidden layer. Keep doing that until the end, right? From the first layer to the last layer. And at the end, we would have this y equal the h of the last layer, and then we would have the loss function of the last layer out. Okay, this is forward propagation. All right. Now, once this is done, then it comes to the next step. The next step is backward propagation. For the backward propagation, we have the loss function. We need to use this loss function to adjust the weight iteratively, start from the output layer, and then iteratively working back to the input layer, working back to each layer and update those parameters. So starting with this, we get the gradient. Gradient is the derivative of the loss, as we all know. And then starting from the last layer to the first layer, we need to convert the gradient on the output on the layer output into the gradient into the pre-nonlinearity activation. Okay, so this is what it's done, right? From the gradient here, g, right? It needs to kind of multiply with the say the weight of it need to kind of we need to compute the derivative of f and ak. AK is from that layer, right? That layer of AK, just like in the last one, right? Okay, so it's the value combination value of that layer, the derivative at that stage, and multiply with gradient. So in that way, we will get g here, and then we use this gradient to update parameter of b and w of that layer. So why do we need to do that? Just remember, gradient that we got is the gradient. I should draw it like this. The initial gradient that we got is the one that is post activation. What you need to do is to compute the gradient of pre-activation, which is just multiply with the derivative of the of the function and with the activation value. And then from that we get g, which can be used to update parameters. It can be used to update parameter for each of the way that is linked to this node. Okay, and once we got that, we can then propagate, right? We can then propagate g back to each node. Okay, so that means g will then propagate back to each node here, and then use again to adjust the parameters of the next layer. So once g is propagate in this case is the update of the value of g, and then we go to the next layer L-1, and then perform the same thing, right, until we reach the layer 1. Right, this is called back propagation. Okay, I will have a simple example to show you on the next slides. Okay, but before that, let me take 10 minutes break. And then we will come back to look at some examples and also to look at the implementation of this feedforward in Keras. Okay, let's take 10 and we will start again maybe 30 minutes. We'll start again on 7:15. Okay, if you have questions, put it into the chat. I will come back and respond to those questions. I'll answer those questions after the break. All right, let's move on to the next one. Okay, so let's take a look at the inside of the network. Here is the diagram showing how for each neuron computes the output. Okay, we have x0 here as as 1 to denote w0 as bias, and we have x1 to xm. These are fetched into the network, which these are fetched into the node, summation node here, which has corresponding weight multiplied to each of the input. And the combination, the new here, is fetched into the function, the squashing function, to compute y. For this one, we have the function as f equals summation of j from 0 to m of wj xj. Then the f function need to have a certain squashing behavior. It can be on-off, it can be ReLU, or it can be this. Let's use sigmoid for now. Okay, it can be the sigmoid function. Now, if it is a sigmoid function, then it has property that we have already mentioned. That is, the function like this, fx equal 1 over 1 plus e to the minus x, would have the derivative as the value itself multiplied by 1 minus the value. Right? This is a nice property, especially when you want to compute the gradient. Okay, so this is the sigmoid function, and the weight comes from the adjusting using the adjustment of the network using sample data. The training is done by presenting the network with sample data and modifying the weight so that it would produce desired output. For each modification, it is called an epoch. One iteration of going through the whole input and adjust the weight is called an epoch of learning. Okay, and for each of the epoch, this will be done. Okay, so the weight are adjusted in this way. For example, for linear transfer function, right, the adjustment would be the learning rate multiplied by the difference between the desired output time output. For sigmoid transfer function, this we have already done this in the derivation of the gradient. This is desired output y and the output, the actual produced output, and the output and 1 minus output time input. Okay, and use this to adjust for the weight. For example, in this perceptron, in this one neuron example, let's say we have this not linear though. We have a certain thresholding transfer function. And in this sense, let's say we have this. The output should be 1 from 1, 0, and 1. But if we were to compute here, the output is 1.3. If assuming that the output threshold is 1/2, then this is correct. Okay. If it's false, say if the output should be 0 instead, then we need to update the weight. Let's say we have a simple number alpha equal 1. Then from the example that we have of the linear gradient, linear transfer function here, this should be 0 minus 1, 0 minus 1, 0 minus 1, and then 1, 0, 1 as input to adjust like this one. And you can see that for the node that contributes to errors, they will be penalized. The weight will be penalized to another direction based on the gradient. Okay, so this has become minus 0.5, this has become minus 0.2, and you can use this new value to compute, and then you see that the value now in total would be adjust to 0. Okay, so then this is how it works in detail. But in the network, you can see that the flow of information has to propagate from output and through the hidden layer and through the input. So in that sense, we need to compute forward and then compute backward. Right, this is just example of how to compute forward. I already explained that. Suppose you have 0 and 1 like this. Put this into multiplication here and adding with the bias, you get H1 at minus 7.6, H2 as 1.8, and then fetch to the output, you get low activation for H1, high activation for H2. And then these H1 and H2 are then fetched to O1 to compute output. Then you get the result out. This is the forward computation. In the back propagation, it need to fetch back, right? You need to use gradient and update the input. I have already covered that. It's like the pretty repetition of the same one. So in terms of pseudocode, we start by initializing the network weight and then starting for each example, starting with the output layer, starting with the forward pass, and then compare it to target. We get error and then pass the delta W to the hidden layer, do the backward pass, okay, and then update the weight and repeat again, okay. So the back propagation is itself is gradient descent because the update of the weight is actually the old weight minus alpha and the derivation of the error function with respect to the weight, the old weight. But this can be changed according to the different strategy to optimize. We will look at this in a lecture called optimization, right? More optimizing the model, which we will look at different strategy to optimize. There are stochastic gradient descent, the one that you have implemented, using the adaptive moment, using other types of learning rate adjustment, which allow you to reach the target quicker, right? For example, learning rate can be adjusted because if it is too small, then it would converge slowly. If it is too large, then it would converge. It might not even be converged. It might go diverging, or it might converge too fast and stuck at local optimum. Okay, so there are other ways to allow. There are other ways to kind of iteratively adjust the weight, like calculating momentum. Taking the old momentum and use it to propel the adjustment using the moment, using the second derivative. So there are other ways to do this, which we will look at that in the optimization lectures. Okay, so in summary, the back propagation this is the old slide. It actually we compute the error and then we fetch the error from the output neuron, having the delta here as the gradient. This is the net and f prom, just like the one that I talked in the first one, multiplied by the difference between the target and the output, and then you can then use this to multiply with the output to get the gradient, and use this to update the layer, and then we can fetch this. We can fetch delta to the previous layer, the one that it fetched to, right? Like working backward. And calculate delta on each layer, and then you calculating the curve E by curve W for each layer. Let's look at some example here for clarity. If we have the output 1 and 1 and then pass through this network, we will look at the two weights, W111 and W211. Okay, and this you can see a pair of number here. This one is like the value before activation function and the value after activation function, okay? So we'll use this to perform the gradient descent, a simple gradient descent here. First, all right, let's look at this piece by piece. Starting with the output here, right? The output is 1. Right, but the value that we have is 0.65. So the difference, the error here is 0.35. This is at this layer. I'm going to draw it here and not deleting it. Okay, try not being confused. Let's change color. This is epsilon 1. So epsilon 1 is here. Then the delta to 1. The delta to 1 is the one that we will use to calculate the update. Okay, the delta to 1 is 0.65 and 1 minus 0.65 and 0.35. And this is the value that you got. This is delta to 1. 0.35 is obviously the error here. So what I'm doing here is to calculate the delta to 1 at this layer. Okay, passing through the activation layer. Right, this is the derivative, right? The activation layer derivative of the net multiplied by the delta. You get the delta before the activation function. Okay, but that's not all, right? Because there is, well, actually we got this already. Okay, we can actually update the node, the weight here, W211. Because the W211 is attaching to this error, this delta. We can use this delta to update the weight by multiplying it with the output, well, actually the input here, right? The output of the previous layer or the input of this layer. So if it's large value, got to penalize, got to update. Small value, not need to update. Okay. Depending on the penalization as well. So for this one, we have this delta 211 equals new here is learning rate multiplied by this. Oops, I shouldn't write like that. Right, multiplied by the delta 21 here and multiplied by the input. Then you get this delta 211. That's for this layer. Okay. Now to compute the delta 111 of the previous layer, right? We need delta at this leg, and we also did delta at this leg, because each of these would contribute the error that occurring at these two ends would come from the same source. So we have to compute delta at both ends in order to kind of propagate the error back. So here we compute for the error 2, this is 0 minus 0.25, 0.65, got this value, then plug this value to get this delta 22, which I will write it here, delta 22. Okay, now it's time to propagate everything back. We can get delta 11, delta 21 and delta 22 to compute the delta 11. And what is the value of delta 11? Delta 11 need to come from error. Think about it, at error at this end. Error at 11. The error at 11 here would equal to the weight of 211 times delta 21 and plus the weight of 211 layer 2 node 1 to node 1, layer 2 node 1 to node 2. Okay, and delta 22. Okay, it will look like this, and then multiply with the activation, right? The derivative of the activation. That's why we have this delta 11 at this layer, delta 11 as the that value and the derivative. Okay, derivative of the activation function to get the pre-activation error. That's delta 11 here, delta 11, and then we can use delta 11 to update the weight of the W111 here, right, by using delta 11 multiplying by the input side, which is 1 here, and you can use this to update the network. All right. This is how backpropagation work. Okay. So all the weight will be calculated, right? And after the update, we repeat the process again. Right? All the weight are initialized, and then we perform feed forward, calculating delta, perform feedback, backward propagation, calculating the delta, and then use them to update the weight of the whole network, and then repeat doing that again many times until the model converge to the point that is able to remember the patterns. Now we will look at examples on how to train the model using Keras. Right? So let me switch to Keras here. Let me clear it first. Actually, I don't remember whether I have installed. That. Never mind. So here is the example of text classification using IMDb to perform sentiment analysis. Okay. So obviously load the Keras dataset IMDb, and then I don't know. I might have not installed the libraries. I haven't installed library, but let's just try anyway. So and then load the IMDb dataset. Okay, should be fine. Load the IMDb dataset afterward. Then let's take a look at example. These are the word vector denoted as number, and the label that this is 0. To decode the content, we need to obtain the dictionary, and then from the word index here. Then use word index mapping with the indexes to get the sentences out. Okay, and then we can see this is the word index. Then map the word index with the trained data. You got the decoded review like this. Bad music, giant safety pin, whatever. Here, okay. So now we are going to prepare the data for training, right? So we'll do the backward style. The trained data, the first trained data is 218, second is 189. So we will pad the sequence so that we have like a fixed size document. In this case, we are going to use like one document, I would say one line per document as the backward style. Okay, so if it contains that word, it will be 1. Actually, there is like count binarizer that can be utilized as well in scikit-learn or other libraries that are available here. So in the end, we have like xtrain equal 25,000 document, 25,000 reviews, and 1,000 as the dimension of word here, number of word that we kind of capture. I did not clean the based on frequency. I just take 1,000 word here. And here is the first example. You can see that this is a vector of word, and it contains like whether it contains that word or not. And this is for y. For y, we also have this similar dimension. Let's take a look at the value of y train. 0 and 1 as well to denote the positive, negative sentiment. Then let's train the model. So these are the data that we use in training the model. To train the model, we need to create like the feedforward style layer, right? So what I'm doing here is like the old script to import from Keras. Well, you can use TensorFlow and then use Keras for that. This is the old one that I prepare. For this one, I use a sequential API or sequential. What should I say? The sequential method. That is the model method which we will use later on. The model API that allow you to configure the flow of the network in more intricate detail. For this one, we are going to just use simple sequential layer and sequential model, and then add to that. So we have the sequential model here, and then we can stack for each layer, right? Starting from the first layer here, we specify input shape as 1000, and using ReLU activation size, the number of nodes 16, and also 16 here, and the output is 1 as a sigmoid to the node 0 and 1 output. Very simple. Just stack the model. This is a very simple model. All right. Then run. Here there are 160,000 parameters, trainable parameters. Okay. Then we need to specify the optimizer, right? We will talk in more detail about the optimizer. What is RMS prop? What is ADAM? What is NADAM? We will talk about different types of optimizer in the, I think, the next lecture, if I remember correctly, but I'm not sure, but should be, right? Specify the optimizer. Done. Also here, specify the loss function and the metrics that we use in training the model, right? In looking at the result here. And then we here I did not and actually there are many ways to do this. You can do the cross validation. You can ask the model to split it for you, but here I split the data out as the validation set, right? Validation set, and then use it to train here model fit of the partial X train, partial Y train, and then number of epoch, the batch size. The batch size here means that it will batch the calculation. So it will calculate gradient, accumulate the number of the gradient, and then update the model once the accumulation is done. And this is the validation set. Okay. Partial train. Oh, I forgot to run the above here. Oops. It might take a little bit long. Long time than I expect. The GPU is not available. But well, training at the same time as using this Zoom certainly takes certain tools here, and also I run other things besides this as well, right? Encoding of video and other stuff during this as well, so it takes quite some time. Right, so let's wait until it is finished. For each iteration, you can see that here we have the number of the epoch number and the sample that it used. So because we batch size 200, so it it would batch the total size to 200 and then use it for training. And we have the loss function, the loss value, the accuracy, the validation loss, validation accuracy. You can use this to trace whether the model has overfitted or not. If the validation loss, decreased, validation accuracy decreased, then it indicates certain overfitting. If the accuracy increased, the training accuracy increased, the validation accuracy decreased, then you can see the divergence between the two. Then that indicates that it is overfitted. Done. Then let's take a look at the error. Okay. Here's the plot of the loss value and the validation loss value. You can see that after just some number of epoch here, you can see that validation loss increase afterward. This obviously indicate the overfitting because I did not specify any types of regularization to make the model less overfitted. You can see that it is easy to get the model that is overfit here. For this one, the plot of accuracy, it would tell the same story, that for validation accuracy, it peaked around like 3 epoch, and then afterward it is overfitted, right? Just that. So we, 4 epoch would do. Train it with 4 epoch using the whole data set and using model.evaluate to evaluate the result. Okay, done. Model.evaluate to evaluate the result. Okay, we got accuracy of 0.88 here. You can use this to predict the output using model.predict. It would predict the label. As probability. Then you can use threshold to select the value of that. There are other example here as well, but I'm going to leave it to you guys. First one is binary classification. The second one here is multi-class classification. You can take a look at how we specify the multi-class here. And the last one here is for regression. For regression here is use Boston housing. Similar, they are quite similar, but the difference would be in terms of the output layer. For this one, the output layer and the loss function here. Loss function here, the first one, loss function is categorical cross entropy for multi-class, binary cross entropy for binary class, and just MSE, right, for linear class, linear function to predict. Well, I suppose you can take a look at this code to see into the detail on how to build the Keras feedforward model using this one, right? In terms of the mathematical calculation, you can see how backpropagation work. And the next time we will take a look at the optimization, the way that you can adjust. Actually, I shouldn't say optimization, although it's called optimizer. It is actually the way that you can adjust the weights. You can adjust the learning rate of the gradient, because by have different way to adjusting the learning rate of the gradient, you can make the model to be optimized slowly or very fast, or behave differently. And that is what we will look at next time. Okay, so yeah, this is the end of this lecture. Do you have any questions that you would like to ask? You can put it into the chat or turn on the microphone. Or if you have question, feel free to post into the group. Okay, mathematically, today is comparable to last time, I suppose, but it will be more structural, right, in terms of the propagation of the error. What I want you to understand and able to understand for this lecture is in terms of the algorithm, the backpropagation algorithm, because it plays very crucial role in understanding the deep learning architecture in the further model, like in recurrent neural network. You understand what is the vanishing gradient, the exploding gradient, and that's by understanding backpropagation and how it works, and also why residual network that has been proposed, comparing in the model like convolutional neural network. Right? There's a proposal called ResNet. Why it is better? Why it works better than the simple convolutional network? It is because of the flow of the gradient. Is the key here. Okay, and also next time when we look at different optimizer, you see the difference in terms of how fast it moves by controlling the learning rate. All right. If there's no question, let's call it a night, and see you next time, 6 p.m. again. Right. So stay safe. Have a good night. See you next time.